Welcome to the pre-lab for experimentally determining enthalpy. Expectations, there will be 4 videos, including this one, for the pre-lab. Each video should be between 2 and 5 minutes. The first 3 videos include example problems, including this one. Make sure to include them in your notes. Then there'll be some questions that you will fill in on the foldable and some quizzes, guiding questions to help complete the front of the foldable and to be prepared for the lab. During this lab, our goal will be to determine the delta H of reaction for the following reaction. Mg plus oxygen gas yields MgO. So basically the burning of magnesium. This we cannot directly measure experimentally because of the heat that it occurs at. However, we will be using Hess's law that we'll be talking about in this video in order to determine the delta H of this reaction. In order to do so, we will first have to determine the delta H of reaction for various other reactions using bond energies, the heat of formation, and an experiment. First, Hess's law. Hess's law is essentially the algebra of chemical reactions. Just like in math class, you may have done systems of equations where you can add them up, eliminate the common terms on both sides. Same thing will apply for Hess's law. We're going to take multiple equations and we will add them up in order to get the reaction we want. Couple things of note for some of the algebra. We can reverse the reaction. So we can flip it so that the products are now the reactants. And if we do so, the enthalpy is going to be the opposite sign. We're used to this with reversible reactions. An endothermic reaction in the positive direction is exothermic in the reverse direction. Also, we can multiply or divide the reaction, and if we do so, then we will multiply or divide the delta H. And then if the reactant is on the product side also, we can cancel them out, similar to like terms. Let's take a look at an example. So this is our equation we are wanting to figure out our delta H for. Notice sometimes we'll have a fractional coefficient. Just go with it. I know it looks a little bit odd. And then we are given 2 different equations. So we are going to manipulate these equations so that way we can add them together to find the delta H of that equation, because we know these delta H's. They are given to us. So I'm going to walk you through basically the application of these rules. Then in class, we will walk through the Hess's law process for the reaction we are trying to get. So first thing I'm going to do is equation 2. I'm going to flip it. So reactants become products, products become reactants, and you will notice my sign also switches. The reason why I did that is I want to get my chlorine gas on the product side, so it matches with the top equation. Then, right now I have 3 chlorine gas, and I have basically 2.5 up there. So I'm going to need to reduce down. That will also help me get rid of my 2p. And so I'm going to do so by dividing by 2. Notice now my delta H is also divided by 2. So I took this equation, divided everything by 2. Then if I add equation number 1 and add these 2 up, I will take these, and they're going to be on my reactant side, and I'm going to take these, and they're going to be my product side. Since I'm adding those all together, I'll also add my delta H's. And it will look like so. Notice I have some that are already crossed out. That's our like terms. So I have phosphorus trichloride on this side and the same number of phosphorus trichloride on my product side. So those two will eliminate because they cancel since I have 1 and 1. So now I have phosphorus pentachloride yields phosphorus solid plus 2/3 chlorine gas plus another mole of chlorine gas. So I can combine these like terms together and I will end up getting my 5/2. And then I can also add together my delta H's to get my final reaction. It's a bit of problem solving. We will work through the example in class for the experiment that we will be conducting.